All right. Yeah, let's get started. Welcome to PyData St. Louis, everyone. We um, Thank you so much for our speaker, Advitya. He's going to talk on LLM-driven merge conflict resolution. And Advitya, the floor is all yours.
Awesome. Yeah. Thanks so much for having me here, Ayush. And yeah, hi everyone, and thanks for joining. My name is Advitya Gemawat. I am a ML engineer with Microsoft in Windows. And today I'll be chatting about LLM-driven merge conflict resolution. In a way, y'all could argue this might be my response to the age-old interviewing question, tell me about a time you had a conflict. In terms of the agenda items, so I'm planning to go over the problem space and existing landscape of merge conflicts across software projects, what exists today, limitations and things. Then I will continue to talk about the different insights that I've gotten to learn in terms of customizing LLMs for this particular task, and also other insights that might be useful for other LLM projects. And keeping up with the PyData theme of the talk, I will also end with a few hopefully bite-sized tips and tricks around how y'all can potentially use some of these coding principles and design principles into your own projects. And so above all that, I really hope this will be fun for the audience listening. And so while we're on the topic of fun, I think it's only natural that I start with the most boring and annoying concept in the software development lifecycle, merge conflicts. I think back when I was interning in college and I was working on this open source machine learning library, contributing some features for deep learning use cases, my biggest challenge in that internship wasn't actually like implementing some hyperparameter tuning algorithms for deep learning use cases. The most challenging part of my internship, where I literally needed handholding, was solving merge conflicts, where I would just like feel shell-shocked. I would loop my teammates in and I would just tell them, hey, I don't understand like these incoming changes over here. I don't understand these like weird looking conflict markers. I don't know what the developer who made this change is intending in terms of functionality. I don't know how to fix these merge conflicts. Even using tooling at that time, like Vim on terminal, was really not intuitive to me. And one of my learnings in that internship back in college was these merge conflicts can get quite a bit complicated, especially these semantic conflicts that require a certain level of logical resolution to actually ascertain the intent of the incoming change and what that developer is intending to do. And how do you sort of address this so-called conflict in priorities between your change or your functionality versus the incoming recently implemented functionality? In a study of 143-ish, I think, open source projects out there, 1 in every 5 code merges causes conflicts. This percentage, like these conflicts, are not going away anytime soon, even in the era of agentic coding. Even in open source datasets like Agentic Flicked, which I believe includes merge conflicts from over 142K plus agentic PRs, even that dataset found a 27% conflict rate. So even in the era of agentic coding, these conflicts are not going away anywhere anytime soon. It takes an average of 6 minutes to resolve a conflict, including understanding it and resolving the conflict and testing your changes. At worst, it can take days. 75% of all merge conflicts are actually semantic conflicts that require some level of logical reasoning to fix those conflicts, not just like code, or not just like variable formatting. Code that is part of merge conflicts is 2x more likely to have bugs, and code that is part of these like semantic part of these resolutions of semantic conflicts is exponentially more likely to introduce bugs down the road. I will let y'all in on a little secret, or I guess an open secret here. LLMs don't know how to fix merge conflicts in their pre-training. Even though there are now these AI-based conflict resolution capabilities that exist in several modern coding agents, the UX is great, the accuracy is not. The UX is great in terms of automating these routine or simplistic conflict resolutions, but these features haven't really been very well performant when it comes to a lot of semantic conflicts. And the reason is coding agents, or AI, is very skilled at syntactically merging code, but it's really only you, the developer, who knows what the code should do. Knowledge can be compartmentalized in terms of upcoming feature plans and intended behavior about upcoming feature changes and code changes. And aside from just the lack of knowledge on upcoming features, it's really difficult for these coding agents to ascertain the intent of certain changes. These vanilla models under the hood don't really know the specific unique resolution patterns or these historical conflict resolution patterns of your specific repository. And there's a reason behind this. And what I would argue is an eye-opening reason behind this. Even if your coding agent is able to index a repo, even if that coding agent is commit aware in terms of doing that, even that is not going to help, because a conflicting file is not even a traditional part of Git history. The reason behind this is a conflicting file, at least in Git, isn't really a part of like Git history. It's like an intermediate or incomplete state of a file that needs to be resolved and addressed. When developers pull code, which leads to merge conflicts, when developers pull code, what they're doing is Git under the hood is using a merge strategy or a merge algorithm. Git can be configured to use like different types of merge algorithms. And let's say there's a default behind it. If developers configure their Git to use different merge strategies or different merge algorithms, that can in fact render different kinds of conflict markers on your same conflicting file, because different merge algorithms try to merge the diffs of the file in different ways using different kinds of diff or merge algorithms. And getting wrong AI resolutions can really end up slowing down development down the road. On kind of a humorous aside, a friend of mine had commented early this year in one of our group chats saying that, hey, they were using this coding agent to resolve merge conflicts. And let's just say, looking at their quote, that they did not have an exactly pleasant experience in terms of resolving these merge conflicts. I retracted the name of the coding agents because I didn't want to badmouth anyone. But I've seen this kind of feedback and frustration by developers in terms of their domain-specific merge conflicts time and time again. Here's why this matters. At the scale of really large software projects, merge conflicts don't just bog down developers in their day-to-day. It can lead to massive delays during CI/CD and release. It can even lead to regressions in prod. From my experience, like looking at merge conflicts in essentially the largest Git repo on the planet, the Windows OS repo, I have seen merge conflicts in multiple digits occurring every week in one part. Like every week, domain experts might be split across time zones, and it would take even the most experienced engineers, let's say like 24 to 48 hours, to resolve the sheer volume of merge conflicts. And if there are any build failures after any of those merge conflicts, if any of those conflicts are resolved incorrectly, that is going to take even more time to kind of patch fixes for those. And it can even take up to like 20% of the total developer time of some of the most senior engineers from what I've seen and learned. And so to kind of resolve the level of conflicts here at scale in such a large software project like Windows, we kind of set out to work on how do we customize LLMs and sort of set up evals to teach merge conflict resolutions to an LLM, and to teach these human conflict resolution patterns to a model. Turns out this is a quintessential fine-tuning use case, where thanks to the thousands of historical merge conflict resolutions that we had done by a human, we were able to prep our training data to be labeled. We were able to format our data to have an input with, let's say, a starting prompt describing the problem space and what needs to be done by the model, passing in the conflicting file, and having the model kind of output a resolved version of the file with a friendly explanation. And we were able to utilize, let's say, we were able to utilize models like GPT-5 to, let's say, generate some of those explanations by passing them both the conflicting file and the resolved file. So in a way, you could argue this is weak supervision or knowledge distillation. And then we were able to utilize the Azure OpenAI fine-tuning service to essentially fine-tune an OpenAI model, get its fine-tuned variant, and deploy it in our internal systems. This is also a very interesting challenge from a UX perspective, in the sense of rendering AI resolution or certain code changes that are only made by the UI, only made by AI, which may not be reflected as is in the lineage of the different changes coming from the source, target, or base versions of the file. Because of the complexity of our use cases and the complexity of how conflicts were resolved in the Windows code base, kind of making clear how AI is kind of combining the different lineage of changes from source, target, base version of the file, and then which changes is the AI making by itself, was also an interesting UX challenge in terms of making sure the user experience is intuitive and sticky enough for users to adopt and start utilizing and accelerating their conflict resolutions. Next, I would love to touch upon a few broad stroke insights around teaching a new task like merge conflict resolution to LLMs. I think the first and probably the most obvious insight is that using fine-tuned models is a lot more accurate than using base models out here. What I've seen LLMs particularly shine at is learning these deterministic patterns, where for a variety of files, such as a variety of config files, which might have a whole bunch of different build numbers, different config numbers, those can be really tricky and a lot of grunt work for humans to manually resolve. But LLMs have really kind of shined at it and have proven really strong in terms of the exact match accuracy when we try to compare the LLM outputted resolved code and the ground truth resolved file and do like a strict string equal to with them to make sure that those exactly match. LLMs have also really excelled at these logical and even at like token level, like variable changes in these logical code rearrangements. For example, if there's this new if block that is coming in from one one source or from one direction, and let's say you have a memory cleanup line coming in from another direction, the model has been able to accurately determine that, hey, this memory cleanup line should go below the if condition or like after it. Another insight that I got to learn when we were formulating this problem statement in terms of the input and output contracts to the model was that resolving merge conflicts at a file level is actually much more performant than at a conflict level. The reason is a single conflicting file can contain multiple conflict markers, and oftentimes for these semantic conflicts, code might need to be modified or the developer might need to modify code outside of the bounds of those config markers to ensure that the final code is actually like structurally correct and compiles correctly. And making those changes accurately, especially those changes outside of the bounds of the config markers, involves following these coding patterns, which are very, let's say, specific or proprietary to an internal code base like that of Windows, where these kinds of like very specific coding patterns are just not seen in open source repositories. And so by passing in an entire file, the model also gets to learn the domain-specific coding patterns of, let's say, the internal repo that we're using, and be able to emulate those when it's actually suggesting resolutions. Another really critical insight, which I believe might also be really helpful in perhaps your own LLM projects, is I really got to learn that we really cannot depend on these probabilistic models to do all the heavy lifting for us in terms of accuracy and performance. It is critically important to have deterministic safeguards baked into your overall solution. As some of us might already know, LLMs typically suffer from this age-old problem called the needle in the haystack problem. And when I say age-old, I mean in the context of LLMs, where if a model is applied with a really huge amount of context, that model is susceptible to forgetting certain needles or certain minor pieces of context, which are somewhere in the middle of like a whole bunch of context. And we've actually seen this during inferencing while deploying our solution in our internal systems, where the model can occasionally miss certain lines of code, often in the center of specific kinds of config files and such. And so it is very important to highlight those diffs to the user in terms of what kinds of changes the AI is trying to make, and make sure that there are appropriate human reviews in place to catch any of those errors ahead of time. Additionally, we have also seen a few code formatting errors while the model would try to generate a resolved version of the file, where sometimes the model can mess up formatting around adding extraneous new lines, sometimes shifting the indentations of a variety of lines of code or a variety of code blocks, or even dealing with code wrapping issues when one line of code might be wrapped around or kind of distributed across multiple lines. And so let's say if there is a line of code which is kind of if there's like a single, let's say, line of code divided or wrapped across multiple lines in your editor, even if there's like an extra parentheses that the LLM initially generates, right? Because it generates these tokens in sequence, it's possible that even just generating one extra parentheses can result in compilation errors and build breaks. And so it again becomes very critically important to highlight any changes performed by the LLM, which may not be emulated in the same way in the source, target, or base versions of the file, or in the lineage of that file. In terms of setting up continuous evals as we try to deploy the solution and try to monitor it, the most obvious metric that we initially had was, like I had mentioned a couple of slides back, exact match, which basically involved taking the LLM output of the result file and taking the ground truth result file and just doing like a string equal to with them to see if the results exactly matched with how humans had resolved that conflict in the past. But exact match has a very strong limitation, that it's very sensitive to non-logical changes. For example, sometimes we have seen in the source and target versions of the files that they might have slightly different linting for essentially the same functional code. Or perhaps there may be changes in code comments between like what the LLM outputted versus the ground truth resolution, which are non-logical changes, right? They don't change the functionality of the file. And so to mitigate this sensitivity towards non-logical or even spurious changes in some cases for exact match, the mitigation that we got to try was crafting really tailored text similarity-oriented metrics, where we would utilize text similarity to measure the amount of diffs or changes that are required to perform to resolve a conflict, and how many of those diffs or changes were performed correctly versus incorrectly by your model. Finally, keeping up with the PyData theme of the talk, I will dive into a few bite-sized tips and tricks in terms of your coding practices and design practices. First, I really like using structured outputs. I believe structured outputs is available in both the OpenAI SDK and the Anthropic SDK as well. So structured outputs is a feature which pegs the output of your model to be of a very specific format using JSON schemas or pedantic types in Python. And so what I really like about structured outputs is not only like by pegging my model's outputs to be of a very specific schema, not only is it a lot easier to consume the outputs of the model downstream, using structured outputs in a similar format also brings in a lot of discipline in how we prep our fine-tuning data set in terms of prepping our training and validation data sets and teaching the model to always output its resolutions in the specific format that we want to use during inference time as well. But also a very interesting con that we found is if you take a fine-tuned model like this, which is specifically fine-tuned to generate tokens in a very specific format, and if you try to add this fine-tuned model deployment, let's say an Azure deployment, to some existing coding agent, that coding agent may not be able to utilize this model accurately in terms of all of its tool use. The reason behind that is coding agents typically have these file editing tools under the hood. And so whenever they are using a model or a model deployment, they're kind of using that model to, under the hood, generate a variety of intermediate outputs of different kinds of formats. And so a fine-tuned model just wouldn't be like geared enough to generate all of those intermediate outputs in those different formats. And so some of the default tool usage in terms of reading files, in terms of editing files and such, or even running the search tool natively offered under the hood, these kinds of tool calls might just start failing, and you might get some spurious token outputs if you use a fine-tuned model with a coding agent. So this is kind of an interesting trade-off that I saw with using a solution like this. If there's one thing that I would have done differently in my Python coding implementation, I wish I had researched the best frameworks for my implementation ahead of time before having my coding agent proceed with implementing my solution. Back when I was trying to have my coding agent implement all the scaffolding in terms of the solution, where it would take a particular conflict, make some Azure DevOps API calls to fetch the source and target and base version of that file, and then generate that conflict in our backend, and then pass that to the LLM. Sure, the coding agent was able to use the generic Python requests module to basically make all the correct Azure DevOps API calls, being able to parse the JSON of the API response and trap errors and things. But it was much later when I actually saw that, hey, there's an official API SDK that exists out there, literally called Azure DevOps, which can abstract away all of these request calls and parsing the response and trapping errors into one or very few lines of code, and basically abstract all of this away from us. And so this is where I really got to learn that, sure, coding agents can generate a lot of this API scaffolding for you, but it may not pick the best Python module or framework for your job. This is a design choice. And so design choices are really something where like you really don't want to just offload that to an agent. Looking up like latest best practices of implementing things is really going to help you, let's say, prompt your coding agent better, or supplying it with all the right context for it to make changes that can be more enterprise grade. I am not done with my rant. Your coding agent is not going to tell you this. When I was using a coding agent to generate an Azure function to orchestrate, let's say, generating the config markers or generating the conflicting version of the file and invoking my fine-tuned model, the coding agent implemented my Azure function with the V1 SDK by default, which involved taking up this dependency on this Azure storage blob module and adding this separate JSON file with these JSON bindings in order to load, let's say, your blob or your queue and these kinds of storage artifacts. And then I got to, and when I started to look up some of the latest coding practices around this, I saw, hey, it looks like there's a latest V2 SDK for Azure Functions that basically abstracts away all of this like setup code into like one line Python decorators, which will be so much easier to maintain and also removes this extraneous Azure storage blob dependency. And there's a reason behind why this happened. There's a reason behind why the coding agent chose to implement, let's say, my Azure function using the older V1 SDK by default and not the latest V2 SDK. It is possible if the knowledge checkpoint of your model is, let's say, relatively older, it's quite possible that it might be generating code which is relatively older as well. Like, even if the knowledge checkpoint of your model is latest enough, we also have to realize that in a lot of the pre-training of these models, a lot of the code that was involved in pre-training is likely, well, older code in time in terms of older framework versions and things. And so this really made me realize that we really have to be in control of our design decisions. I'm not talking about going from 0 to 1 here in terms of natural language to building a full app. I'm talking about writing production-grade code that is actually maintainable and scalable. Vibe coding is not enterprise-grade. In fact, shameless plug, I also had written this piece for VentureBeat, kind of exposing all of these ways in which these coding agents are great for 0 to 1 sort of scaffolding, but they may not be production-ready in terms of the quality of code that they write, both from a scalability perspective and from a security perspective. How many of y'all remember Yusuf Dikek, this Turkish Olympian who got a silver medal? Yusuf Dikek has nothing to do with this presentation. This is just for meme purposes out here. But let me share some context around this specific insight. So it turns out there are some service limitations in Azure OpenAI fine-tuning models where my fine-tuned model had a service limit of only being able to output 16,000 maximum output tokens in a single inference call. So that was its maximum context length. Now, 16K tokens roughly translates to 2,000 lines of code in a file, which seems great, right? Because most coding files are not as huge as 2,000 lines of code. But when we're dealing with a decades-old software project like Windows, I have seen coding files north of 10,000 lines of code. I've even seen coding files that are so huge that they actually evaluate to over 150,000 tokens just in that file. And so those file contents are just way too huge to be generated by the model and way too expensive, even if the model is able to generate it in a single shot and coherently. And so to tackle some of these cases, we initially kind of realized that because of the service limits of our model, we can probably it's probably wiser to not have the model just fail and truncate its response beyond the 16K limit, but to actually count the number of tokens in our input ahead of time. And if the number of tokens in our input exceeds 16K, then we can just fail in a friendly way. And so for that, well, there's a technically correct way of counting your tokens. And then there is a very close approximation of counting your tokens. I actually got this insight from a friend who was working on a next edit suggestion feature, where that friend of mine mentioned that, especially in English, this length of prompt divided by 4 is a pretty close approximation towards counting the tokens of your particular input. And it can shave off up to hundreds of milliseconds, which can be especially valuable in latency-constrained applications. And with that, I think I am done with my spiel. Happy to connect across my social media accounts and very happy to answer questions as well. Thank you for listening.
Thank you so much, Advitya. Like Advitya said, it's now open for questions. If anyone has any questions, please go ahead. So if no questions, I guess sometimes, even with me, sometimes re-watching or people sometimes reach back after a talk is done. I do that a lot. Thank you so much again, Advitya, for joining us here today. Please feel free to get connected with Advitya on different social media platforms. And with that, I think we can conclude our event. Let me stop recording.